Okay, so now we're recording. I'll pick up where I left off last time, talking about fixed point iteration. Okay, now I hope I have a better piece of chalk than this, because this is bad. This is much better. All right, so very quick review of things. That the actual iteration, solving x equals g of x, which is just a transformation of the original equation to be handed f of x equals 0. And I'll talk about how you do that transformation. That's on today's agenda. So the algorithm, choose x naught, and then you have a loop. Each new x is just g evaluated at the old x, and you keep going until it converges, if it converges. That's it. That's the whole algorithm. And you would check for convergence, but that's the gist. And there are conditions for existence of a solution x star, which is referred to as the fixed point. And that was g is continuous on an interval, and g maps the interval into itself. So that guarantees that a fixed point is there to find. And then there was a condition for uniqueness and convergence. Okay. Oh. Okay. That if you choose the initial guess in this interval that has a fixed point, and g is Lipschitz continuous, in that interval, where the Lipschitz constant needs to be less than 1. Then you choose any initial guess in the interval, it's guaranteed to converge. Also, the fixed point is unique. And an equivalent condition in the case of derivative, if g is known to be differentiable, is if the absolute value of the derivative is bounded by this constant, this Lipschitz constant L, that is less than 1 on AB. All right, so the function must be continuous. It doesn't have to be differentiable, but if it is, then you have a more convenient condition. Okay. Now, we're going to carry out an actual fixed point iteration now, just as an example. So we're going to solve x equal cosine x. And this is your g. G is just cosine. And we're going to look at the interval 0 to 1. Because if you look at how the graph of cosine behaves, it starts out at 1, at x equals 0, and it goes down to 0 at pi over 2, and in decimal, what is pi over 2 roughly equal to?
Just
Not
3.14, not, yeah. But that's
half of that.
1.1. It's
And you call yourself graduate students.
something. 1.0167.
God, no.
No, that's a 1.5. Oh, wait, what's
Were you
that?
here to chime in?
1.56. 1.60.
Warmer.
1.57.
Yes.
Oh.
That's exactly.
1.57.
To two decimal places. Yes. 1.57.
Oh, 3.14. Okay.
Yes.
None.
Okay. Oh, I see. You took 3 divided by 2 and rounded down. So, yeah.
Yeah.
Okay. All right. So if we limit ourselves, but since this is greater than 1 and cosine is positive up to this point, so if I just cut off at 0, 1, then we can say that cosine does in fact map 0, 1 into itself. So any of these values of cosine, if x is between 0, 1, cosine is between 0, 1. It doesn't have to fit like a glove. It doesn't have to take up the whole interval. We don't care about that. As long as the values of the function g fit within that interval ab, that's good enough. So a fixed point exists. So if I were to draw the line y equals x, there's an intersection. So we know that from a theory, but if you looked at the graphs, you'd see it too, and you could get an idea of roughly where it is. Now, from a graph, you can see the fixed point is unique, but also we can look at the derivative. So g prime, absolute value, well, g prime is minus sine. So now sine is between minus 1 and 1, but if you look at the graph of sine x on 0, 1, it starts out at 0. Eventually, it's going to get to 1. But over here, it is strictly less than 1. Well, actually, I can go further. It's an absolute value is an increasing function. So it's bounded by this at the right endpoint, and that is less than 1. Okay, so this is your Lipschitz constant L. And since the Lipschitz constant in this case is less than L, we know if you don't have the graph, you still know that the fixed point is unique, and fixed point iteration will converge to it. Okay. So, now how many of you have a convenient calculator like the one on my phone? Andy? Okay. Because what you can do is you can try to tell it yourself. I'm going to choose initial guess. So I can choose anything between 0 and 1. I'll just choose 1/2. Okay. Okay. Now, so what you can do on your calculator, at least mine has a cosine button, and hope yours does too. So I put in 0.5, and then you can just keep hitting cosine until the cows come home. I almost said calcine, believe it or not. So if you do, and just be careful to keep hitting cosine, not hitting a neighboring button. Whoops. Before you do though, make sure you are in radian mode. Because like right now by default it's in degrees. And that didn't work so well. So now I'm in radians. Okay, so now you keep hitting cosine, and it's going to bounce around some, like the 0.6 something, 0.8 something. But if you keep going many, many times, you'll see it start to converge, like around 0.739. So x star is roughly, I'll keep going until its decimal places start to stabilize. Okay. 39085, etc. And I just can keep going until nothing changes. I get like several decimal places if I hold it this way. Okay, so 5. 1, 3, 3, 2, 1, 5, 1, 6, something. Keeps going back and forth between 0 and 1. So that is a fixed point, and fixed point iteration converged to it. I just had to keep plugging my x value into cosine a gazillion times. Now, but the thing is, it still took a lot of iterations. It'd be nice to see faster convergence than that. So we're going to handle on why was convergence pretty slow? Because we're going to see from other methods in this chapter that we can solve equations like these performing maybe just 5 or 6 iterations if we go about it the right way. So, okay, so I'm going to leave this here because I'm going to need it later. But what I want to do now is we're going to step back a bit and just look at how to analyze the convergence behavior of root-finding methods like fixed point iteration in general. This will come back to help us later when we talk about other methods like Newton's method, secant method, and so on. And that will give us some insight as to why we had to punch that cosine button quite a few times to get the convergence that we did. Okay. So, jargon time. Very important term is order of convergence. All right, so if you have any iterative method for finding a root of an equation, the order of convergence is a number R such that the limit as number of iterations, k, goes to infinity, the ratio of errors, so xk plus 1 minus x star, over, so error after k plus 1 iterations over the previous error, xk minus x star, raised to the rth power, is equal to some strictly positive constant. And I guess I did kind of left that out of my definition of my notes here. Oh, well, actually, I do need that requirement, but not yet. Now is not the time for that. So,
is this the one in the book, not this book, but the American House book that says if c equals 1, then...
yes. Oh, from 460? Yes, exactly that. Good memory. Okay. So this limit has to exist. So for now, let's say that it must be finite. Now, yeah, so there are certain subterms, if you will, that come with a specific order of convergence. So first, if we have, if r equals 1, and the constant c is strictly positive. It was tempting to use programming speak and say equals equals, because this is an if statement, but yeah, better not. Well, I guess it's not the worst thing to do in this crowd, but still, under these circumstances, the convergence of this method is linear. Okay. So what happens there is there's, in the limit as k goes to infinity, there's a fixed ratio of errors, at least an absolute value. And we'll see that actually happens in fixed point iteration. And in this case, we have another definition. The rate of convergence is, I'll call it rho, and it's minus natural log to base 10 of c.
Isn't it c is between 0 and 1? Is that what?
Oh.
Sorry, I'm looking at your notes.
Yeah, it does. Okay, yes, it does need to be between 0 and 1.
Okay.
Okay. Yeah, so I was thinking about the case where c equals 0 was separate, but okay. Yeah, because if c is greater than 1, your error is actually going to grow. Yeah. I'm glad someone's following my notes even more than I am holding them in my hand. Okay. It's been a long day. Okay. Now, a way that you can interpret the... stop it. Oh. Oh, kill me now.
You need a timeout.
Yes, I do. I was like, why is the table doing that? It never does that before. Okay. Now, the interpretation of rho, that is the number of decimal digits that are of your correct answer that are gained per iteration. So, for instance, if c is equal to 0.1, so 1/100th, then rho would be equal to 2. And so you would get 2 new decimal places correct each iteration. Okay. Oh, there's also a term for c. C is called the asymptotic error constant. Okay. Now, be very careful about order of convergence versus rate of convergence. They're two separate things. They're related, as we see, but they're different. In fact, the textbook for the other numerical analysis class, 46461, by Asher and Greif that we just used, in an early draft, I had to pop them on this. They got the two terms mixed up. And certainly students can from time to time too, so don't do that. Most of the time, we talk about order of convergence, because rate of convergence doesn't really have any meaning unless it's linear. So, okay. Now, other forms of convergence are if r is still equal to 1 and c is 0, so 0 limit is allowed, or we have r is strictly between 1 and 2 and c is a positive constant. So you can have non-integer powers, that's possible. In that case, we say that the convergence is superlinear. Okay. So faster than linear. And then other kinds of convergence, if r is equal to 2, then we say the convergence is quadratic. And there's no requirement that c be less than 1 anymore. We do need c to be less than 1 for linear convergence, otherwise your error might grow. And you don't have convergence at all. But for quadratic, or higher order, it's not necessary. And then r equals 3 when we have cubic, and so on. So like quartic for r equals 4, blah, blah, blah. Unfortunately, we're not going to see any methods in this course that are better than quadratic, although you will have an idea of how you could devise them. Okay, so...
Excuse me.
Yeah.
Could you please show these in plot, like how error goes? Like, I mean, super linear, I cannot believe. I mean, I know that you're saying it's actually converging faster, but I mean, for me, how I could distinguish super linear with linear?
Okay, because I'm going to talk about how fixed point iteration is generally linear, but the way, the distinction won't become clear enough until we see more methods. But quickly I can give you an idea. If you were to try a method and see it converging, when a method converges linearly, the number of correct decimal digits you get per iteration is a constant. If you were to watch the digits converge or see your error, you would see the error go to 0 kind of like at a fixed rate. Whether very slow or very fast, but still a fixed rate. Whereas in the case of a quadratically convergent iteration, r equals 2, the number of correct decimal digits roughly doubles. from one iteration to the next. So the convergence accelerates. So you would see like 4 decimal digits correct, then 8, then 16, and then you're done because you have full precision. It's lightning fast compared to linear. So linear iterations, you could see easily taking like 50-something iterations to converge or more, whereas a quadratic method would be like maybe around 5 iterations and you're done. Superlinear is somewhere in between. The number of correct decimal digits would not double, but it would still increase by like for instance, secant method, the order of convergence is the golden ratio, 1.618, etc. So you'd see the number of decimal digits increase at a faster rate, but not quite doubling. So that's visually, that's how you can tell. So like if you have no idea about a method, you don't see any analysis, and you just run it, from how rapidly the decimal digits converge, you can get an idea of what kind of method it is. And yeah, we will see more concrete examples of this as we go. But okay. Now, all right. Okay, so now I want to take a look at fixed point iteration specifically and how we can tell what order of convergence it has. Okay. And we're going to assume that your function g is sufficiently differentiable, because we're going to use Taylor expansions to carry out this analysis. Okay. So we're going to assume that G is so if all the, including on top of all the other assumptions we've been making, we'll assume that G is continuously differentiable on our interval AB. Okay. So using the mean value theorem, way back in calculus 1, we can say that, so I can define the error after k iterations is xk minus x star. Okay. So I want to relate ek plus 1, the error after k plus 1 iterations, to ek, the error after k iterations. So I want to see how the error changes from one iteration to the next. So ek plus 1 is xk plus 1 minus x star. But xk plus 1 is g of xk, because that's how the iteration proceeds. And x star is equal to g of x star, because x star is a fixed point. So now by the mean value theorem, this is the same as g prime at some unknown point, which I'll call ck, or squiggly, times xk minus x star. Because that's how the mean value theorem works. F of b minus f of a over b minus a is equal to f prime of c. Okay. So c is some unknown point between a and b. So that's what's happening here, that this point is between xk and x star. Okay. But xk minus x star is just ek. So we can see what happens to the error from one iteration to the next. It's multiplied by g prime at some unknown point. That's why we want g prime to be less than 1 in absolute value, to ensure the error is going to shrink. So now I can say that, so if I take a look at the limit, as k goes to infinity of ek plus 1 over ek, and I'll say this explicitly, raised to the first power. So in other words, my order convergence I'm claiming is equal to 1, and I can say that because this limit is, that's going to be the limit as k goes to infinity of g prime of this unknown point, ck. But the error is decreasing from iteration to iteration because we're assuming that the derivative is less than or equal to some Lipschitz constant L, which is less than 1 on AB. So that alone is enough to conclude that convergence is going to happen. This error is going to go to 0. But what does this converge to? Because xck is between xk and x star. What is xk converging to? X star. So this is between them. It's also converging to x star. So it's g prime at x star. So this is C, the asymptotic error constant. And because g prime is bounded by 1 in absolute value, bounded away from 1 in absolute value on the whole interval, then this is certainly going to be less than 1 as well. It's going to be less than or equal to L, in fact, whatever L is. Okay. All right. So this gives you like the ratio of errors. So for instance, if this was equal to 1/2, we'd say the error is being cut in half from one iteration to the next. Okay. So any questions about this? All right. So now, let's return to our example involving cosine. And thankfully, I still have it up. So for g of x being cosine x, my c is the absolute value of minus sine at the root, the fixed point. So like 0.739, etc. So if I go ahead and take that fixed point, plug it into my derivative, and I hit sine, I get 0.6736, etc. So it's not very small. It's a little more than 2/3. So the error is decreasing by a factor of roughly 2/3 from one iteration to the next. So in other words, it's not going to 0 very rapidly. So not only is it linear convergence, which isn't fast, it's slow linear convergence. So that was kind of unfortunate.
Excuse me, how do you get a 2/3?
Oh, well, I'm very rough approximation of 2/3.
Oh, okay.
Yeah. Well. Okay. Yeah, so if your constant c turns out to be greater than 1/2, then this is maybe not the best method to use, because we're going to see another method later, bisection, that cuts the error roughly in half from one iteration to the next. You might as well use that. Okay, and that's known as a very slow method. What can be done here is to try to change the equation into an equivalent one with different g, and see if convergence can be sped up that way. And I'm trying to see if I can remember off the top of my head, because for my textbook that I'm working on, I actually did change this example to something that. Oh wait, no, that was a slightly different problem. Okay. Okay. Do I have time? Yeah, why not? Because I also have Wednesday, but I'm going to see if, like, on the fly, I can change this equation x equals cosine x to an equivalent one for which convergence will be faster, especially since we know what it's supposed to converge to. And I honestly have no idea if this is going to work, but it's worth a shot. And here's what this is based on, because if you were to try this, like initial guess of 0.5, and you keep hitting cosine, 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 what you may have noticed is that, actually I have a picture from the notes, how it bounced around. So you might think, well, maybe the average of successive iterates would converge more rapidly. So we change x equal cosine x to equivalent equation where okay, so xk plus 1 is equal to cosine of xk. So what if I try instead because I'd like to maybe xk plus cosine xk over 2 maybe? Although I have to make sure that whatever I do, that the two equations are equivalent. So for instance, if x equals cosine x, then it's a solution. So, well, in this case, if I take, yeah, that will work. Okay, because let's see. Yeah, if x is equal to cosine x, if I make a substitution, then I get identity. Same thing on both sides of the equation.
Really fast.
What? Oh, it was? Okay. All right. Well, okay, let's check it out. So I'll do the same initial guess. X0 is equal to 0.5. So then x1 is 0.5 plus cosine 0.5 all over 2. Okay. So I have 0.5 cosine plus 0.5 all over 2. And that's 0.68879. Okay, so then if I do this again, well, all right, so 0.68879. Unfortunately, I'm not retaining enough decimal places, but plus 68879. Okay, divided by 2 equals 0.7304. That's already very close. Like, because it was supposed to be 0.73.
Yeah, it took me 12 times to get there.
Okay, so it's better. So, but to get ideas of, let's so our new g is x plus cosine x over 2. So let's look at the derivative. G prime is 1 minus sine x over 2. So now if I take my fixed point, so I'll go ahead and quickly recompute that by hitting cosine a zillion times. Okay, so then I take sine of that, and then add 1, and then divide by 2. So g prime at x star is 1.6 or 0.1632. So the asymptotic error constant is about a quarter of a previous one. So it's going to converge in like 1/4 the number of iterations. So 12, I can see why. So if you reduce the C, then you can speed up convergence. And actually, I had an example in my, so it's really my 460 notes, where I stumbled across an example where the original equation converged very slowly, and I chose a combination like this to kind of cancel out the slope. So it's like a slope canceling form. What? Yeah, it's basically equivalent to the secant method. Yeah, it converges super linearly because it's if you do it that way, yeah, it really is much faster. Okay, now so we got pages all over the place. All right. Now, yeah, so that's one way to choose your G to speed up. Because if you have an idea of where the root is, you can make a derivative small near the root, you'll get faster convergence. Okay. Now, the derivative can also explain how the iteration can fail to converge. And so this example, which actually is taken from the textbook for the other numerical analysis course, the one by Asher and Greif, can help explain what can go right and what can go wrong with fixed point iteration. So if I have this function, g of x is equal to x squared plus 3 over 16. So then if you go ahead and solve the equation, x equals g of x. So there's a quadratic equation. So you get two solutions, two fixed points. So one of them is 1/4, and the other is 3/4. So if you look at a derivative at these two fixed points, so what would the derivatives be? Yeah, just plugging in those specific values. Mm-hmm.
The derivative, right?
Yeah,
That would be 2 times x if x is 3.
yeah. So we get 1/2, but
Plus
it's
3. Oh, plus 3/16. Oh wait, the derivative. 3/8. No.
No.
3/2.
Yes.
3/2.
Yes. Multiply by 2 like you did the first time.
Yeah.
Okay. I know. It's been a long day. All right. So we have a problem here. But this one, it's greater than 1. So if you were to try fixed point iteration on this, if you try initial guess near 1/4, this will converge just fine. So it's actually interesting to try this example out. So for this one, if you choose your initial guess to be less than 3/4, it will converge to the other one. So you can start like at 0.74999 or something like that, and it'll slide away from 3/4. It'll be like, no, I'm backing away from you, and then start towards the other one. So this is basically repelling the iterates. On the other hand, if you choose x naught to be greater than 3/4, it doesn't converge at all. Heads off to infinity. Because derivative keeps getting bigger and bigger past that point. So it is not possible to have fixed point iteration converge to 3/4 unless you choose your initial guess to be 3/4. You're sitting right on top of it. But what's the point of that? So this is very important to keep in mind how important that derivative is. Okay. Which pages have I not covered yet?
We're on page 15.
Yes, I'm trying to find page 15 up here.
Oh.
Got it. Okay. All right. So we have a term for these. So this one is called a stable fixed point, and the other one is unstable. Okay, so I have a theorem in the notes that if the derivative at the unstable at a fixed point is strictly greater than 1, like it is here, then that would be, so it's an unstable fixed point, and a fixed point iteration will not converge to it except in a finite number of iterations. So basically, if you get lucky, that's the only way. So you have to choose like just the right kind of initial guess. Not necessarily sitting right on top of it, but in a way that just, depending on the G, it'll just happen to put you there. So in other words, it's just not a good idea. So basically, you have a bad fixed point function, because what's happening is, as you saw, the new error is multiplied by the previous error. Well, if the derivative is greater, and that it's multiplied by the previous error times the derivative. If that derivative is greater than 1, then the error is actually going to increase. So that's why things can go wrong in that case. Okay. Now, okay, so fixed point. Generally speaking, so unless you get lucky, will not converge to such a fixed point. So you want to have a stable one. Okay. Now, there's one other case that still needs to be discussed. Because, so for that, I'm going to go back to expanding G. So in this case, instead of using a mean value theorem, we'll go a little bit further, so I need to use a Taylor expansion. Okay. So suppose we have this situation. So I have ek plus 1, as before, is g of xk minus g of x star. So we're repeating a previous analysis, but this is g prime at x star times ek. So this is a Taylor expansion centered at x star. So all derivatives are going to be evaluated at x star. So the next term in the Taylor expansion is going to be 1/2 g double prime at x star ek squared, and then this would continue. Okay. So what we've already seen is if we can make g prime at x star, or g prime near the fixed point small, convergence is going to be more rapid. So let's take that to the extreme. What if g prime at x star equals 0? What's going to happen to the convergence in that case? And this Taylor expansion reveals the answer. Not everything. Because we're only talking about the derivative at that specific point. So g prime is not going to be 0 in general. Well, that'd be a constant function. But,
So what, is the error 0?
no. Because we're trying to find a relationship between the new error and the previous error. So in general, when we have this term, we have a linear relationship between them, where this one is proportional to the previous one, and this is your proportionality constant. But if g prime is 0, what is it?
Same? I don't know.
Okay, someone else?
Yeah.
I read the answer.
Cheater.
No, I'm just saying that.
Okay.
I read it. Sorry.
Anyone else want to put something out there?
We have nothing to compare, right?
What?
We have nothing to compare. If
Well, but the thing is, if g prime is 0, then this can still be non-zero. So this term is gone.
It's, sorry.
Well, you know the answer. So.
I know.
All right, well, we have 500 people who have not. So.
So you said those don't have to be zero?
Right, so in fact, let's go ahead and assume that G double prime at X star is non-zero. And this is now this is a lower order term, so really the focus needs to be on this.
Second order, right?
Yeah, quadratic convergence. Yeah, so because now we're saying that EK plus 1 over EK squared is 1/2 G double prime at X star in a limit. K goes to infinity. So that is your C. And we have quadratic convergence. And because when you have a function having its derivative equals 0 at a certain point, that doesn't say anything about whether any other derivative is going to be 0 at that point. Okay. Do you see where it's coming from now? Oh, okay.
We had 560C answered this question.
Oh,
I
okay.
remember.
Well, that was a while ago. Almost a year ago. Okay. I still sense some confusion still, maybe, or not. Because it's the higher the power of EK, because EK is small. So the higher powers of EK are going to be negligible compared to lower orders. So normally, this is the dominant term. But if this is 0, it makes the whole term go away. This is a dominant term now. So what if G prime and G double prime are equal to 0? Then what happens to the convergence?
Cubic convergence.
Yes, cubic convergence. And this would be the C, or absolute value would be the C in that case. Okay. All right, so we'd like to have that situation where G prime at fixed point happens to equal 0, but how do you ensure that? Okay. Although in fact, what we could do is construct a method to guarantee that, and I'm going to use the rest of this time to sort of work my way to that point where we can have that kind of a method in general. Okay, but so the thing is, fixed point iteration is generally linearly convergent, but we can have these exceptions. Okay. And because it's quadratic convergence, we don't care if this 1/2 G double prime is less than 1. It doesn't have to be for convergence. Okay. Now, one of the last things we need to cover in fixed point iteration is, I haven't really said much about how do you choose, if you have an f of x equals 0, that's your equation. How do we choose the g? We transform f of x equals 0 to x equals g of x. We have some flexibility there. How can we use that flexibility? So okay. And I'm going to use an example to illustrate how things can go wrong and how you can fix them. So, for example, x plus natural log of x is 0. So, of course, the most obvious way to rewrite this in x equals g of x form is to have this be your g minus natural log of x. So what you can do is, if you were to graph this function, what you would find is, from a graph, x star, it has one root, and it lies somewhere between 0.5 and 0.6. So let's take a look at the derivative then What is G prime in this case?
-1/x.
Yeah, -1/x. So now, so if we look at this interval, 0.5 to 0.6, how big is the derivative going to get on that interval? How big is this derivative going to get on this interval? Because we know we need to look here. Yeah, so we get values that are greater than 1 in absolute value. So, so we only care about absolute value. So this is greater than 1 on this interval. So in other words, whatever fixed point we have is unstable. So we cannot use this G. If we try fixed point iteration with it, it's not going to work. Okay. Now, so here's what we can do. Because if x equals g of x, and suppose if the function g is invertible, I can apply g inverse of x to both sides. But then the right side simplifies to just x. So g and the g inverse cancel out. So, so we can try x equals g inverse as our fixed point for a fixed point iteration. So let's see what that would be in this case. So if y is equal to minus natural log of x, I want to solve for x as a function of y to get the inverse. So how would I solve this for x? Yeah, use the exponential. Now first let's move a minus over to the other side. Okay, yeah, now you take the exponential of both sides. So e to the minus y is equal to x. So that is your inverse. So our new fixed point iteration is e to the minus x. Okay. All right, now, the thing is, why should that work? And this actually came up last class. What is the derivative of the inverse function?
1/.
Yes.
Derivative, the absolute value of the derivative.
Well, not absolute value, but so derivative of the inverse is 1/f prime of f inverse. So if the derivative of this g is too large, the derivative of a new g will be small because we're taking reciprocal of it. So if the original g is greater than 1 absolute value, this will definitely be less than 1 absolute value. And if you plug x values like 0.5 and 0.6 into this, yeah, that's exactly what will happen. So this one works. So if you choose like maybe 0.55 or something as an initial guess, and you keep doing e to the minus x to it, it will converge. It's not going to converge all that fast, but it will work. Okay. So that's one thing to keep in mind is that you can, if you choose a g and it's not a good g, if you can invert it, then that will fix your problem. But another thing is to have a template for g of x. What you can always do is, so if f of x equals 0, you can say so this is true if and only if x is equal to x minus some function phi of x times f of x. So this is your g, provided that that phi of x should be non-zero, at least near x star, because you don't want to get a false positive. For instance, you could choose phi to be a non-zero constant, and that would definitely make sure that any solution of this equation would be a solution of your original equation. All right. Okay. But yeah, certainly, if this wants to share a root with f, that's fine. That wouldn't matter. So this is, so that's allowed, but it should not be 0 anywhere else near the root. Okay. All right. How am I doing on time?
6 o'clock.
Okay. So what I can do is I'm contemplating that, but well,
Let us out early and we will meditate on the algorithm of mixed configuration.
yeah, I'm so sure that's exactly what would happen.
I feel like I've been in here for that's because we're meeting here. That's all.
Fixed point meditation.
Yeah, exactly.
Alright, let's do that.
Okay. Shoot. I just realized there's one other thing that I kind of skipped over in this section, and the question is, do I really need to cover it? Because I really don't want to. Okay, well, okay. So one thing I want to point you to, page 13, there's analysis of a number of iterations needed for convergence. So it's using like the Lipschitz condition for convergence. Okay, like for instance, if you want to get the error below a certain point, like epsilon, then how can you find a number of iterations that will get you to that point? So it's basically just some algebra. It's not very interesting. It's not nearly as interesting as the other thing that I am looking at. That will perfectly set up Wednesday's class. Okay, it's just one page of notes. So I'll just finish off frying your brains, and then we will definitely be out of time then. Am I still recording? I better be. Yes, I am. Good. Because I had to change windows. Okay. All right, so this will finish you off.
Is that 13 of your notes in the book?
What?
13 of your notes in the book.
Notes. It's in the book, in that same section. Okay. Yeah, I didn't print out this page here. Okay, so I'm going to do a variation of what I just described called relaxation. I'll try to digest this probably anything but relaxing. So g of x is going to be x minus a constant lambda times f of x. So this is my phi, but I'm just letting phi be a constant. So the idea is how to choose lambda to make convergence as rapid as possible. Okay. So the way you're going to do that is, okay. I'm going to assume that the derivative at the root is equal to some value alpha and it's positive. Okay, so because when this derivative is 0 at the root, it's a double root, that causes problems for numerical methods. But we're not going to deal with that difficult situation right now. So what that means is, because the derivative is positive at this point, that means that f prime is positive on an interval containing. So I'm going to assume that f prime is continuous. So by continuity, if it's positive at this point, it's going to be positive near that point. So I have some interval, x star minus delta, x star plus delta. So as long as I choose delta that's small enough, the derivative is going to be positive. Okay. And in fact, I can say on this interval, f prime is bounded below by some constant little m, bounded above by some constant big M. And both of these constants are positive. So again, this is all because of continuity of f prime. That's one of those good to know things. If a function's non-zero at a point, by continuity it's going to be non-zero sufficiently near that point. Okay, so now this is my g. Therefore, my g prime is 1 minus lambda f prime. So, but now I know something about how f prime is bounded. So I can say that g prime, well, if I mess with this, I get 1 minus lambda f prime is bounded above by 1 minus lambda little m, bounded above by 1 minus lambda big M. So now I have constraints on g prime. And the thing is, keep in mind, g prime, I want it to be less than 1 in absolute value. Now, if I want g prime to be constrained in such a way that its absolute value is as small as possible, I want these bounds to be negatives of each other. So I'm going to set this equal to k, and I want this to be equal to minus k. Because remember, I can choose lambda. So I can say 1 minus lambda big M is equal to minus 1 minus lambda little m. And I can use this to solve for lambda. Because I have minus 1 plus lambda m. So I can rearrange this, and I won't do the algebra here because of time, but lambda turns out to be 2 over little m plus big M. So this is like an optimal value of lambda, that to make these guys as small as possible. And if I go ahead and use this lambda back in here, I have a g prime in absolute value, which is bounded above by k. And the value of k, by plugging back in here and there, is going to be big M minus little m over big M plus little m. So again, that's just the algebra. I won't work that out here. Okay. But here's the nice part. Big M, little m are positive. Also, big M is bigger than little m. So yeah, the numerator is positive too, but because it's a minus here and a plus down here, it's less than 1. And it's because big M is bigger than little m. Okay. All right. Now, so now I am, so that way I've guaranteed convergence of fixed point iteration by finding a lambda that makes this work, as long as I'm close enough to the fixed point. But the other thing is, if I look at, suppose I have x inside this interval. So it's between x star minus delta and x star plus delta. x minus x star therefore is less than or equal to delta. So it's in this, from being in this interval. So now, if I take g of both sides, so g of x minus g of x star, which equals x star because it's a fixed point, well, that is going to be, that's going to be bounded, it's less than or equal to k times x minus x star by mean value theorem. So what that means is what this is saying is if x is in the interval, this interval, I'll call this capital I, that means that g of x is also in that same interval. And the reason why that's important is to ensure existence of a fixed point. G has to map an interval into itself. So anything that's in this interval is like we have a radius delta and a center x star. So x is within that radius of x star. G of x is also within that radius of x star. Okay. So fixed point. So a fixed point is guaranteed to at least exist. So because that's something that has to be checked too. Now, so in other words, if we have a situation where we have a non-zero derivative at the root of f, we can choose, there exists a lambda that makes convergence as rapid as possible. Now, the reason why I'm showing you all this is, notice we have, as k goes to infinity, this value of lambda converges to, well, these are derivative values. These are balanced in a derivative. So as you're converging to x star, delta, if you let delta go to 0, then these converge to f prime of x star. So lambda converges to 2 over f prime and x star plus f prime and x star. But you simplify this, you get 1 over f prime and x star. And what happens to k is these two values, big M and little m, are converging to each other.
I'm sorry, 2 over, is that f prime x star plus f prime x star?
Yeah, same thing.
Okay.
So if these guys, big M and little m, are converging to each other, what happens to k? What does k go to? No,
Oh, wait, what?
this.
Oh, just kidding.
All right. So big M and little m are converging to each other.
Oh, so 0?
Yeah, because we have big M minus little m. Yeah, so the numerator is going to 0. So, you're bound. Unfortunate choice of notation.
Yeah, that's what.
Okay. And the number of iterations goes to infinity. K is going to 0. Okay. But the thing is, if a derivative is going to 0 at the root, what kind of convergence is that? As discussed about 15 minutes ago. Quadratic convergence. So,
Yeah, Cash, what's up? Sorry.
okay.
Somebody gotta take them to this place.
All right. So to wrap up, we can use lambda equal 1 over f prime at xk, for instance. So now, here I'm holding lambda fixed for all iterations. But I can let lambda vary. If I let lambda equal 1 over f prime of xk, we get quadratic convergence, at least in the limit, as the number of iterations goes to infinity. So I can use lambda k here. So each iteration. So now my method becomes xk plus 1 is g of xk, and that would be xk minus f of xk, I know this is awful board usage on my part, but at least everything's here. So now this is my iteration. So I started by letting lambda be fixed, but now I'm going to let it vary, and I'm just about out of time. But does anyone recognize what this is?
Yeah. Newtons.
Yes, this is Newton's method. And I'll spend more time on this on Wednesday, all about Newton's method. But Newton's method is a special form of fixed point iteration set up to achieve quadratic convergence. So if you want to use this relaxation, the ideal relaxation parameter, this is a very frequent idea used in solving nonlinear equations, or even some systems of linear equations. The best way is to use 1 over a derivative. So that speeds up convergence, and we'll see when we talk about Newton's method, it speeds it up quite dramatically. Yeah.
Why did we get how we get quadratic convergence?
Oh, just because your derivative at the root is going to 0. Because by choosing 1 over, because of this.
So, I mean, why not super linear?
Because it's going to drive g prime all the way to 0. But we're going to do a separate analysis to show you why Newton's is quadratic.
Oh, okay.
Yeah, it's not as obvious from here. It's just that here it's only because we're driving this to 0. And I know it suggests superlinear, but we'll see how it's actually quadratic in general. Yeah. Okay.